In this video, we will talk about a very important Calculus 2 skill, which is evaluating substitution integrals without having to work through all of the steps of U substitution. Take a look at these various integrals that are written here. Each one of them is an integration by substitution problem. For instance, with this first one, we have the cosine of 2x. We would choose u equals 2x. We'd follow the steps of substitution. For this second integral, e to the 1 plus x, we would choose u to be 1 plus x, work through the steps. And every single one of these, we should be proficient at solving using substitution. However, they are about the simplest type of substitution problems that we could have, and we want to be able to solve them without having to work through all of the steps of U substitution. So some people call this the guess and check technique. Essentially, the thought is we'll try to evaluate the integral without having to write down all the steps of substitution, and then when we've written down what we think is the answer, we want to double check by taking a derivative that our answer is correct. The key is that we want to be thinking about reversing the chain rule. So let's try this first one. We have the integral of cosine of 2x. Here's my guess. Well, I know that the antiderivative of cosine is positive sine, so I'm going to start there. And I'm going to think about taking the derivative of this using chain rule, and I want to get back to cosine of 2x. So I would need to have sine of 2x, and if I just leave it at that, when I take the derivative using chain rule, I would have cosine of 2x times the derivative of 2x, which is 2. So if I just use this as the antiderivative, I would have an extra multiple of 2 out front. Well, I don't want that. So I compensate by dividing by 2. All right, now let me double check. And this checking step is extremely important because as we become more proficient with this way of solving integrals, we can tend to get a little bit overconfident, and if we forget to check, we might make some assumptions that are not valid. So checking the answer after we've thought about the antiderivative is critical. So we want to take the derivative of sine of 2x over 2. Sometimes it's sufficient even to just do a mental check, and as we work through more problems, we'll just think of doing a mental check here. All right, well, dividing by 2 is just multiplying by 1/2. That's a constant multiple, so we can take that out. And we have the derivative of sine of 2x. Use the chain rule now. The derivative of sine, cosine. And inside the parentheses, we use the inner function 2x. And now we multiply by the derivative of the inner function. The derivative of 2x is 2. These cancel. We have cosine of 2x, exactly what we wanted. We'd want to add a plus c here for the antiderivative, but this is the correct answer. Let's try the second integral here. We have the integral of e to the 1 plus x power. I'm going to guess that the antiderivative is an exponential function, e to a power. So I'll guess e to the 1 plus x power. Now again, checking, even just mentally, is incredibly important here. If I take the derivative of e to the 1 plus x, I need to use the chain rule. E to the 1 plus x has a derivative of e to the 1 plus x times the derivative of 1 plus x, which is 1. So we do indeed obtain the original function. Add plus c, and we have the correct antiderivative. We won't take the time to write down the check for each of these problems, but at least mentally, we want to think of taking the derivative of our answers and making sure that they correspond with the original integrand. All right, how about this -3 divided by x plus 2? Well, if we take the antiderivative of 1 over x, that's the natural log. And this function looks sort of close to that. If we were to follow through all the steps of U substitution, we would choose u equals the denominator. And if you want to double check that on your own, I encourage you to do so. But we want to take the antiderivative here without having to work through all of those steps. So this function looks sort of like 1 over x. So we would guess here an antiderivative. Well, we have the -3 out front. And then the antiderivative of 1 over x is natural log. So we would guess natural log absolute value, x plus 2. Now mentally, think of taking the derivative. The derivative of natural log of x plus 2 is 1 over x plus 2. From the chain rule, we just multiply by the derivative of x plus 2, which is 1. This is the correct antiderivative. Let's take a look at the next one. We have the integral of e to the -x. Well, the antiderivative of e to the x is e to the x. So we'll start with writing e to the -x here, and we're tempted to leave it there. But let's think about the derivative of e to the negative x. Let's actually write down the procedure for this one. The derivative of e to the negative x, we need to apply the chain rule. We take the derivative of the exponential function, which is e to the negative x, times the derivative of the inner function. The inner function here is negative x. That has a derivative of negative 1. So we would multiply by negative 1. So if I just choose e to the negative x as the antiderivative, I don't get the correct answer when I check by taking derivatives. So to compensate, I would add a negative out front, and now this is correct. Let's take a look at the next integral. We have the integral of 1 over 3x minus 1. This looks like 1 over x, that sort of a form. So we'll use the natural log function here. This will be natural log, absolute value of 3x minus 1. And if we think of taking derivatives here, we would have a multiple of 3 after applying the chain rule. In order to compensate, we divide by 3. That's the correct antiderivative for that integral. How about the next one? It's a similar problem. However, this time, the derivative of the denominator here would be negative 2. So I would write 5 times the natural log, absolute value, 4 minus 2x, plus c. Now, when I take derivatives of this using chain rule, I would have multiplying by negative 2 from the inner function. So to compensate, I divide by negative 2. That's the correct answer for that problem. How about this next one? This looks a little more involved. But notice that 3x squared is the derivative of x cubed. So if we think of reversing the chain rule here, we would take the antiderivative of sine, that's negative cosine, and then I'll just write x cubed, and I'll write down the check for this one. If we take the derivative of negative cosine of x cubed, I have negative the derivative of cosine, which is negative sine, so positive sine of x cubed times the derivative of the inner function. This is again using chain rule, 3x squared. Yes, indeed, we get what we started with. All right, this next one, this is once again a little bit more involved. It might not be a bad idea to work through all the steps of the substitution here. We would choose u to be the denominator, and we could work through the steps. But if we notice, the numerator is a multiple of the derivative of x squared, which is 2x. So this is going to be a natural log antiderivative. We have the natural log, absolute value of 3 plus x squared. Then taking derivatives to check, we would have a multiple of 2x. We only want a multiple of x. So to compensate, we divide by 2. Let's write out the check for this one. This is a little bit more difficult to see. We want to think of the derivative of our answer here. The derivative of natural log is 1 divided by the inner function. And now according to chain rule, multiply by the derivative of that inner function. The derivative of 3 plus x squared is 2x. The 2's cancel. And we have x divided by 3 plus x squared, which is exactly what we wanted. One more problem, and then we'll talk about some common misconceptions that we can fall into if we're not careful. We have the square root of 5x. Now, if we know the antiderivative of the square root, that's most of the problem here. We can think of the square root as raising to the 1/2 power. So the antiderivative would increase the power by 1 and divide by the new power 3/2 or multiply by 2/3. All right, but instead of having x, I have 5x. So I want to put a 5x in the parentheses. And then when I take the derivative using chain rule, I would have an extra multiple of 5. So I compensate by dividing by 5. Add a plus c, and that's the answer. I encourage you to double check, take the derivative of this answer, and you'll see that it's the square root of 5x. Now, as we become more confident with this concept of working through substitution problems without following all the steps of substitution, just by this guess and check method, as we become more proficient, we might fall into certain pitfalls. For instance, take a look at this problem, the integral of 2 divided by 4 plus x squared. Now at first, this might look like a natural log antiderivative. We have this sort of a form where we have a fraction and we have x's downstairs. So we might guess that the antiderivative would be something along the lines of 2 times the natural log of 4 plus x squared. But if we think of checking, take the derivative of this, which is 2 times 1 divided by 4 plus x squared times 2x. Now notice, we don't have a multiple of x in the numerator, so this guess for the antiderivative is not correct. The antiderivative of this function actually involves an arctangent. We won't discuss it, but the point of this example is that sometimes as we become a little bit better at this method, we need to watch out for mistakes where we make assumptions and forget to check the answer to guarantee that we're finding the correct antiderivative. So I encourage you to develop your proficiency at these sorts of integrals. The important part is to always check your answer by differentiating your guess and double check that you get the correct answer. Here's a list of problems that I would suggest that you work through. Each one of these problems can be solved using integration by substitution without having to go through all the steps. You can check your answers by taking derivatives. This will help you become more proficient at taking integrals.